planet where diamonds fall from the sky. Sounds unreal, right? But it actually exists, and it could be the most priceless gem mine in the universe. Also, why the rich are eyeing diamond planets for their next fortune. Will NASA's new telescope discover aliens before 2030? Beyond the well-known orbits of our sun's planets lies a realm of mystery and wonder. Worlds that defy our expectations and push the limits of what we thought possible. These are the exoplanets, planets orbiting stars other than our sun, each with its own story, its own secrets hidden across the vast light years between us and them. From scorching gas giants with atmospheres hotter than stars to frozen worlds trapped in endless ice, these distant planets reveal the mind-blowing diversity of the cosmos. As we journey through the universe, we'll uncover their extreme conditions, bizarre orbits, and the deep mysteries that make them some of the most fascinating objects out there. WASP-12b, a planet being torn apart. WASP-12b isn't a planet that sparks dreams of life. It's a world marked by destruction, a slow-motion tragedy playing out across the cosmos. Located 1,400 light-years from Earth, this exoplanet is on a one-way trip to annihilation, doomed by its fiery closeness to its parent star. A yellow dwarf with a gravitational grip so strong it's ripping the planet apart. WASP-12b's fate isn't some explosive, dramatic end. It's a drawn-out, inevitable unraveling. A stark reminder that in the universe, just like in life, destruction can be as slow as it is unstoppable. Scientists call WASP-12b a hot Jupiter, a gas giant orbiting way too close to its star. That proximity means it's blasted by insane levels of radiation and heat, with surface temperatures soaring over 4,500 degrees Fahrenheit. 2,500 degrees Celsius. Under that kind of punishment, the planet's atmosphere isn't just heating up. It's being torn away. The star's gravity yanks at the planet's gas, siphoning it off into space. Over time, this will leave nothing behind but a ghostly trail of gas and dust spiraling into the star's fiery embrace. This slow, inevitable destruction makes you think, WASP. 12b isn't just a planet, it's a cosmic lesson in impermanence. In the vastness of the universe, nothing lasts forever. WASP-12b's fate stands in stark contrast to the usual cosmic stories of creation and growth. Instead of a world forming and thriving, we're watching one fall apart, forcing us to face the hard truth that everything, no matter how grand or eternal it seems, is temporary. The slow death of WASP-12b is almost like a cosmic metaphor for life itself. Just as the planet is torn apart by forces it can't escape, we too are shaped and eventually undone by time. We're born, we grow, we live, and in the end, we all face our own final chapter. The idea that life is fleeting isn't new, but WASP-12b drives it home in a way that's almost poetic. It shows us that destruction isn't always sudden or violent. Sometimes it's a slow, quiet unraveling. But here's the twist. Even in destruction, there's transformation. As WASP-12b's gas and dust spiral into its star, they don't just vanish. They become part of the star itself, fueling its fire, feeding its light. In a way, the planet's death isn't really an end. It's a change, a shift from one kind of existence to another. That idea hits deep. It means that even when something is completely wiped out, there's still a chance for something new to rise from what's left. And isn't that just like life? We go through our own cycles of loss and rebirth. We break down, we rebuild, we fall apart, only to come back different, but still here. WASP-12b isn't just a dying planet. It's proof that even in the end there's a new beginning. But these moments of destruction are often followed by rebirth, by the rise of something new and unexpected. It's a powerful reminder that destruction isn't the opposite of creation. It's part of it. A necessary step in the never-ending cycle of change and evolution. WASP-12b's fate also highlights the fragility of existence. This planet, once a mighty gas giant, is now being ripped apart by the very star that gave it life. And isn't that just like us? Our lives too are fragile, shaped by forces beyond our control. We're molded by our surroundings, by the people and circumstances around us, just as WASP-12b is shaped by its star's relentless gravity. And like the planet, we're never static. We're always changing, always being reshaped by the world around us, but that fragility isn't something to fear. It's something to embrace. It's a wake-up call that life is precious, that every moment is fleeting and worth holding on to. Just as WASP-12b is slowly unraveling, we're all moving through the stages of our own lives, each day bringing us closer to our inevitable end. Yet in that fragility there's beauty. The beauty of simply existing, of experiencing life in all its forms, even as it slips through our fingers. Redefining endings. WASP-12b also makes us question what an ending really is. We usually think of endings as final, the moment something ceases to be. But WASP-12b flips that idea on its head. Its destruction is an instant. It's a slow fade stretched across time. In a way, the planet's death isn't a single event, but a series of moments, each one inching it closer to its final transformation. This forces us to rethink endings. Maybe they're not full stops, maybe they're transitions, just another step in the universe's endless cycle of change. In the end, WASP-12b's story is the universe's story. A cosmos that never sits still, always shifting, always evolving. It's a humbling reminder that nothing, from the tiniest atom to the mightiest planet, escapes time and change. GJ-1214b is a planet wrapped in mystery. Located 48 light-years from Earth in the constellation Ophiuchus, this world has fascinated scientists since its discovery in 2009. Dubbed a super-Earth, bigger than our planet but smaller than gas giants like Neptune, GJ-1214b stands out for one reason: its thick, hazy atmosphere, which has sparked endless debate. What's hiding beneath those clouds? From the start, GJ-1214b has been a head-scratcher. It orbits a dim red dwarf star, much cooler than our sun, at a distance that could place it in the habitable zone if its atmosphere plays along. What makes GJ-1214b truly special is its thick, soupy atmosphere. So dense we can't see through to the surface. This planetary blindfold has scientists buzzing with theories about what this strange world might be hiding. The most exciting possibility? GJ-1214b might be a complete water world, completely covered by a planet-wide ocean miles deep. The numbers back this up. The planet's lightweight makeup suggests it's packed with water rather than heavy rock or metal. We're talking about a place where water isn't just present, but absolutely everywhere, shaping the entire planet. This raises some mind-blowing possibilities. We know life on Earth needs water. Find water, and you might find life. If GJ-1214b really is all ocean, who's to say something isn't swimming in those pitch-black depths, protected from space's harshness by the planet's thick atmospheric blanket? But with the planet so far away and so hidden, these tantalizing questions will have to wait for answers. The mystery gets even deeper when we look closer. Hubble telescope observations detected signs of water vapor in that thick atmosphere, giving the water world theory some solid support. But here's the twist. Scientists still can't agree on what exactly makes up that hazy shroud. Some think it's steam clouds floating high above an endless ocean. Others argue it could be stranger stuff like hydrogen or methane mixtures. These possibilities paint completely different pictures. A steamy water world with a crushing vapor-filled sky over a bottomless ocean, or a mini Neptune with a thick gas shell hiding a solid core of rock or ice. Either way, GJ1214b isn't giving up its secrets easily, and that's exactly what makes it so fascinating to scientists. Every new discovery about this weird world makes us rethink what planets can be. Alternatively, if methane dominates GJ1214b's atmosphere, we might be looking at a frigid, distant relative of our solar system's gas giants. A world where hydrocarbon hazes swirl in perpetual twilight. Each theory suggests a radically different version of this alien planet. Yet current data keeps all possibilities tantalizingly in play. That impenetrable atmospheric shroud has turned GJ1214b into the ultimate cosmic puzzle. Scientists are essentially planetary detectives forced to work with frustratingly indirect clues. How the atmosphere filters starlight, subtle temperature variations, the way light bends around the world. It's painstaking work where every new observation seems to complicate the mystery rather than solve it. What makes GJ1214b particularly fascinating is how it represents a whole class of mysterious in-between worlds, larger than rocky planets but smaller than gas giants. These super-Earths and mini-Neptunes dominate our galactic neighborhood, yet we understand them least of all. GJ1214b could be hiding revolutionary secrets about how planets form and evolve. Imagine if beneath those clouds lies an unimaginable supercritical ocean where water exists in a bizarre state between liquid and gas, creating a world without clear boundaries between sea and sky. Exotic ices formed under crushing pressures with structures alien to anything on Earth. Atmospheric chemistry playing out on scales that dwarf our entire planet. The very uncertainty surrounding GJ1214b makes it invaluable to science. Whether it's a steamy water world, a hydrocarbon-rich oddity, or something even stranger, this enigmatic planet is forcing us to expand our understanding of what's possible in the universe. Every observation, even those that contradict each other, brings us closer to rewriting the textbooks on planetary science. Another wild theory proposes GJ1214b might be drowning in a global ocean of liquid ammonia or some other exotic chemical cocktail, not water. Picture an alien seascape where the very chemistry of life would need to rewrite the rules. Any organism surviving there would operate on a biology we can barely imagine, potentially using completely different molecular building blocks. This twist makes the planet even more fascinating, forcing us to rethink where and how life might exist in the cosmos. The more we study GJ1214b, the more it defies explanation. Years of research have only deepened the mystery, with each breakthrough revealing fresh puzzles. Just when scientists think they're closing in on answers, the planet throws another curveball. Proof that the universe loves keeping us on our toes. The hunt for truth continues. Cutting-edge tools like the James Webb Space Telescope are our newest allies, peering deeper into that soupy atmosphere than ever before. Yet even with these advances, GJ-1214b seems determined to keep its secrets. There's a growing sense that some mysteries might never fully unravel, that this shrouded world will forever linger at the edge of our understanding. But that's the thrill of it. GJ-1214b isn't just a science project, it's a cosmic wake-up call. It shoves us beyond textbook definitions, daring us to imagine planets, and maybe life, in ways we've never considered. Every question it raises about alien oceans, bizarre atmospheres, or the limits of biology is really about something bigger: our endless quest to decode the universe's secrets. In the end, GJ-1214b's greatest gift isn't answers, it's wonder. A reminder that for all we've learned, the cosmos still holds infinite surprises. And that's what keeps us looking up. The TRAPPIST-1 system represents one of the most remarkable astronomical discoveries of our time, fascinating both researchers and the general public. Located approximately 40 light-years away in the constellation Aquarius, this planetary system stands out for its unique configuration. What makes TRAPPIST-1 extraordinary is its collection of 7 Earth-sized planets all orbiting a single small cool dwarf star. These worlds are packed remarkably close together, with orbits significantly tighter than those in our solar system. Despite their proximity to their host star, several of these planets reside within the habitable zone, that crucial region where liquid water could potentially exist on a planet's surface. The star itself, TRAPPIST-1, is significantly smaller and cooler than our Sun. Its planets, designated TRAPPIST-1b through TRAPPIST-1h, vary in their characteristics. Some appear to be rocky worlds similar to Earth, while others might possess vast oceans or dense atmospheres. This diversity, combined with the potential for habitable conditions, makes the system particularly intriguing for astrobiological research. The system's compact nature creates striking celestial views. From the surface of one planet, neighboring worlds would appear prominently in the sky, with some surface features potentially visible to the naked eye. This close arrangement also leads to complex gravitational interactions, with each planet subtly influencing the other's orbits. Scientists have leveraged these precise orbital dynamics to accurately determine the planet's masses, providing valuable insights into their compositions and atmospheric properties. The discovery of multiple Earth-sized planets, including several in the habitable zone of a single system, has generated significant excitement in the scientific community and opened new avenues in the search for potentially habitable worlds beyond our solar system. The discovery of the TRAPPIST-1 system marks a pivotal moment in astronomy, fundamentally expanding our perspective on planetary systems and the potential for life in the universe. This compact system of 7 Earth-sized worlds orbiting a cool dwarf star presents extraordinary possibilities for astrobiology and planetary science. What makes TRAPPIST-1 particularly significant is the diversity of environments represented among its 7 planets, all orbiting within a space smaller than Mercury's orbit in our solar system. The innermost planet, TRAPPIST-1b, likely experiences extreme temperatures that could create a molten surface with vaporized mineral atmospheres. Moving outward, TRAPPIST-1e occupies the habitable zone and may possess Earth-like characteristics, including potential liquid water and atmospheric conditions suitable for life as we know it. TRAPPIST-1f presents the intriguing possibility of a water world, completely covered by a global ocean where life might exist in deep, dark waters sustained by hydrothermal activity. The outermost planets like TRAPPIST-1G could maintain subsurface oceans beneath icy shells, kept liquid by tidal heating from gravitational interactions with neighboring worlds. The system's compact architecture creates remarkable celestial dynamics. From any planet's surface, neighboring worlds would appear prominently in the sky, some potentially showing discernible features. These close orbits also enable precise measurements of planetary masses and densities through their gravitational interactions. This discovery suggests that compact systems with multiple potentially habitable planets may be common in our galaxy, dramatically increasing the possibilities for finding extraterrestrial life. TRAPPIST-1 serves as both a laboratory for studying planetary formation and evolution, and a beacon in our search for life beyond Earth. The system's accessibility for study, combined with its remarkable features, ensures it will remain a focus of astronomical research for decades to come. The outermost planet, TRAPPIST-1H, is likely a frigid, icy world with a thin atmosphere and barren surface, similar to Mars. Yet even here, life might find a way, perhaps in the form of hardy organisms adapted to the cold and low gravity, conserving every bit of energy and scarce water. This speculation isn't unfounded given life's incredible diversity on Earth, where organisms thrive everywhere from scorching deserts to icy poles and deep ocean trenches. The TRAPPIST-1 system's remarkable feature is its multiple potentially habitable worlds, 3 or 4 compared to our solar system's 1. Each planet could host entirely different ecosystems representing unique chapters in the story of life. This system challenges us to expand our imagination about what life might look like under alien conditions we can scarcely comprehend. Shifting focus to Kepler-16b, located 200 light-years away, we find another extraordinary system. This gas giant orbits 2 stars simultaneously, a sun-like primary star and a smaller, cooler red dwarf. These binary stars, named Kepler-16a and 16b, are locked in a gravitational dance that has lasted billions of years. Remarkably, Kepler-16b maintains a stable near-circular orbit between them, a balancing act of gravitational forces that demonstrates nature's precision. The system embodies cosmic duality, with 2 very different stars working in concert to create a stable environment for their planetary companion. Kepler-16b teaches us that harmony doesn't mean sameness. It's the balance between differences that creates true stability. This planet lives a reality we can hardly picture, with 2 suns lighting its sky instead of 1. Picture standing on its surface, even though it's a gas giant, where you might see both suns shining at once, throwing double shadows across the landscape. One sun rising as the other sets, creating surreal color displays, endless twilight periods as the stars chase each other across the sky. This constant dance of light and shadow makes an alien yet strangely beautiful world. Kepler-16b's twin suns mirror life's own balancing act, between joy and sorrow, love and loss, creation and destruction. The planet shows us that equilibrium comes from managing opposing forces, not choosing between them. Imagine how ancient cultures might have interpreted such skies. They might have seen divine twins representing life's dual nature, eternal lovers chasing through the heavens, sacred moments when the suns aligned or eclipsed with 2 suns. Time itself would work differently. Celebrations might mark when both suns shared the sky, or when one briefly blocked the other. This double-starred sky would have inspired countless stories, reshaping how entire civilizations understood their place in the cosmos. People living under two suns would likely develop a philosophy based on balance and duality. Seeing their twin suns constantly interacting, they'd view life as a series of opposing forces, good and evil, love and hate, joy and sorrow, that need to stay in harmony. Just as their planet maintains perfect balance between two stars, they'd believe personal peace comes from finding equilibrium between life's extremes. The eternal celestial dance above them would serve as the ultimate example of this cosmic balance. Then there's 55 Cancri E, the so-called Diamond Planet. This supersized Earth orbits dangerously close to its star, completing a full revolution every 18 hours while enduring blistering 2,400 degrees Celsius temperatures. What makes this world truly remarkable isn't its extreme heat, but what scientists believe lies beneath its surface. The planet's host star contains unusually high carbon levels, suggesting 55 Cancri A might be packed with crystallized carbon. Diamonds. Imagine a world where the very ground beneath your feet could be solid diamond, where what we consider precious gems might be as common as ordinary stones. This possibility completely upends our earthly notions of value and rarity. While diamonds form through rare, violent processes deep within our planet, on 55 Cancri E, they might make up the bulk of the planet's composition. The existence of such a world forces us to reconsider what we consider truly precious, when the universe can create entire planets out of what we treasure most. What truly holds value in a world where diamonds are as common as dirt? This question forces us to rethink what precious really means. On Earth, diamonds are prized because they're rare, hard to get, and beautiful. But in a universe full of incredible wonders, how do we decide what's truly valuable? If diamonds were everywhere, would we still care about them? Or would they just become ordinary? 55 Cancri A makes us face these questions head-on, shaking up our ideas about wealth and rarity. It shows that value isn't absolute. It depends completely on where and how we find things. Here on Earth, diamonds are special because of how they form and how hard they are to mine. But on a planet like 55 Cancri A, those same conditions might be totally normal, making diamonds no more special than regular rocks. This makes us think bigger. In a universe with diamond planets, ultra-hot stars, and countless galaxies, how do we decide what's truly precious? Maybe real value comes from our experiences with things, not the things themselves. A diamond might be ordinary on 55 Cancri A, but on Earth it represents nature's power, time's passage, and human ideas of beauty. The stories and meaning we give objects might matter more than the objects themselves. This also makes us question our endless hunt for material wealth. Throughout history, people have fought over gold, oil, and diamonds. But what does that mean when whole planets might be made of these materials? In such a vast universe, maybe we should value knowledge, experiences, and connections more than physical possessions. The Diamond Planet challenges us to ask, in a cosmos full of wonders, what's really worth pursuing? The discovery of planets like 55 Cancri A forces us to reconsider what true wealth means. Not just material possessions, but the knowledge and wonder that expand our understanding of existence. Then there's Troius 2b, a planet that defies all expectations. Located 750 light-years away in the constellation Draco, this gas giant holds a chilling distinction. It's the darkest known exoplanet, reflecting less than 1% of the light that touches it. Unlike Jupiter with its bright reflective clouds, Tris 2b is a void. If you floated nearby, it would appear as a black silhouette, darker than charcoal, absorbing nearly all light into its searing, hostile atmosphere. Scientists remain puzzled by its extreme darkness. The planet's atmosphere might be saturated with light-absorbing chemicals like sodium, potassium, or titanium oxide. With temperatures exceeding 1,000 degrees Celsius, no reflective clouds form. Just a swirling, suffocating abyss. Tris 2b isn't merely dark, it feels unnatural, a place where familiar cosmic rules dissolve. This eternal night isn't just a scientific curiosity, it taps into something primal. Darkness has always symbolized the unknown, the fearful, the edges of our understanding. Tris 2b embodies that dread, a physical manifestation of the void, yet its very existence also inspires awe. The universe doesn't just harbor life-giving worlds, it crafts nightmares too. And in that duality we confront a humbling truth. The cosmos owes us neither light nor comfort. It simply is, vast, indifferent, and unimaginably strange. The existence of a planet like Tris 2b shatters our assumptions, forcing us to accept that the universe operates on a scale of strangeness we're only beginning to grasp. It's a visceral reminder that discovery doesn't always comfort. Sometimes it unnerves, pushing us into uncharted intellectual territory where the familiar laws of nature twist into something alien. Then there's Ogle 2005 BLG 390LB, Ogle for short, a frozen behemoth drifting in the void. Located a staggering 21,000 light-years away in Sagittarius, this super-Earth, 5 times our planet's mass, was detected through gravitational microlensing, a feat akin to spotting a needle in a cosmic haystack by its shadow. Ogle isn't just cold. It's a monument to absolute zero. At negative 220 degrees Celsius, its surface is a cryogenic wasteland. Any atmosphere lies frozen into glacial sheets, molecules locked in stasis. Its dim red dwarf star is barely more than a faint ember in the sky, casting perpetual twilight over ice plains that could stretch for continents. This isn't a world, it's a tomb. The mysteries pile up. Did it form this way, or was it hurled into the deep freeze by ancient gravitational chaos? What does ice do under such extreme cold? Could kilometers-thick layers exhibit bizarre properties unseen on Earth? Could anything survive? Not life as we know it, but anything in this cryogenic purgatory. Ogle's existence forces us to confront the sheer variety of planetary nightmares. For every Earth-like world, there's a Tris 2b swallowing light or an Ogle frozen in time. The universe isn't just vast, it's outright hostile to our expectations. And that's what makes these discoveries so thrilling. They're not just answers, they're doorways to darker, deeper questions. These discoveries underscore the staggering diversity of planetary systems in the cosmos. While Ogle 2005 BLG 390LB's frozen wasteland seems utterly hostile to life, we've learned never to underestimate nature's ingenuity. Could some unimaginable form of existence persist in its cryogenic depths? The possibility, however remote, stretches our definition of life itself. This frozen giant embodies the universe's indifference, a world where the very concept of warmth is alien, yet one that obeys the same physical laws as our vibrant Earth. Its existence proves planets can form and endure in realms we'd never thought to search. Shifting from eternal winter to scorching infernos, we encounter HD 209458b, Osiris, a trailblazer in exoplanet science. This gas giant, orbiting just 4 million miles from its star, completes each revolution in a mere 3.5 Earth days. The proximity creates a hellish environment where temperatures approach 1,000 degrees Celsius, causing its atmosphere to swell into a distended gaseous envelope. What makes Osiris revolutionary isn't just its extremes, but how we discovered it. Through the first observed planetary transit in 1999. As it crossed its star's face, astronomers could finally measure an exoplanet's size, mass, and atmospheric composition directly, opening a new era of planetary exploration. Its bloated atmosphere, bleeding into space under the star's relentless fury, presents a stark contrast to Ogil's frozen silence, two bookends of planetary extremes that continue to redefine what's possible in our universe. Osiris presents one of the most dramatic cases of planetary evaporation we've observed. This bloated gas giant, with its diameter 35% larger than Jupiter's, yet only 70% of Jupiter's mass, is literally boiling away into space. The star's intense radiation superheats the upper atmosphere, stripping away layers of gas at staggering rates, a process we can actually witness during its transits. This atmospheric escape created the first concrete proof that exoplanet atmospheres aren't static but dynamic systems shaped by their environments, just like planets in our solar system. The real revolution came when spectroscopy revealed Osiris's atmospheric composition: hydrogen, oxygen, carbon, and sodium, marking the first time we'd ever identified specific elements in an alien world's atmosphere. Most tantalizing was the detection of water vapor, proving that even in this hellish environment, the fundamental building blocks we associate with life exist. While Osiris itself is far too hot for liquid water, this discovery suggested that cooler exoplanets might share similar atmospheric components under more hospitable conditions. As the prototype for transit studies, Osiris established techniques now used to investigate thousands of exoplanets. Its extreme properties, the swollen atmosphere, violent mass loss, and searing temperatures, taught us that close-orbiting planets often endure brutal conditions that fundamentally reshape them over time. This world didn't just expand our catalog of planets. It redefined how we study them, proving that even from 150 light-years away, we can detect the subtle fingerprints of atmospheric chemistry that reveal an exoplanet's history and fate. These discoveries have expanded our knowledge of how planets interact with their stars and how atmospheres evolve over time. Osiris's study revolutionized exoplanet research by proving we could not just detect distant worlds but examine their atmospheres and physical properties in detail. This breakthrough led to advanced observation techniques using ground-based telescopes and space observatories like Hubble and James Webb, bringing us closer to answering fundamental questions about planets and potential life in the universe. Nicknamed Osiris, this planet marked a new era in astronomy, transitioning from simply finding exoplanets to deeply analyzing their atmospheres, environments, and evolutionary forces. Its puffed-up atmosphere and gradual mass loss revealed the incredible diversity of planets and their unique stories, each offering insights into the cosmos and our place within it. Kepler 186f, an Earth-sized planet in the habitable zone. Discovered in 2014 by NASA's Kepler telescope, Kepler 186f made history as the first Earth-sized planet found in its star's habitable zone. The Goldilocks region where liquid water could exist with the right atmospheric conditions. This discovery marked a major milestone in the search for life beyond Earth. Kepler 186f orbits a small, cool red dwarf star about half the Sun's size and mass. Since the star emits less light, the planet likely receives less energy than Earth does, making it cooler, but its actual temperature depends on unknown atmospheric factors. A thick atmosphere with greenhouse gases like carbon dioxide could trap enough heat for liquid water. While we haven't confirmed water or an atmosphere yet, Kepler 186f remains one of the most promising candidates for potential life. Its Earth-like size, just 10% larger in radius, suggests enough gravity to maintain an atmosphere long-term. It completes an orbit every 130 days, placing it on the outer edge of its star's habitable zone. The main challenge? Kepler 186f is 500 light-years away. Current technology can't provide detailed data about its surface or atmosphere, leaving its mysteries and possibilities open for future exploration. Scientists can still gather crucial information by analyzing the starlight that filters through Kepler 186f's atmosphere during transits. This method, called transmission spectroscopy, may reveal atmospheric composition and potential biosignatures. While Kepler 186f receives less stellar energy than Earth, its position in the habitable zone suggests liquid water could exist with a sufficiently dense atmosphere, challenging our traditional views of where life might thrive. This discovery proves Earth-sized planets in habitable zones aren't rare, dramatically improving the odds that life exists elsewhere. The techniques developed to study Kepler 186f directly pave the way for next-generation telescopes like JWST, bringing us closer to answering whether we're alone in the universe. Though 500 light-years away, this world remains a landmark discovery. Proof that planets with Earth-like potential exist even around different types of stars. HD 40307G, a super-Earth in the Goldilocks zone discovered in 2012. HD 40307G stands out as a super-Earth, 7 times our planet's mass, orbiting comfortably within its star's habitable zone. Located just 42 light-years away in Pictor, this world receives comparable energy to Earth from its cooler K-type dwarf star. Its greater mass suggests stronger gravity that could help maintain a protective, life-friendly atmosphere. As part of a 6-planet system, HD 40307G offers astronomers a nearby laboratory to study multi-planet dynamics and habitable zone evolution. Future telescopes may directly analyze its atmosphere, making it one of our best candidates to search for extraterrestrial life. The planet's location in the habitable zone means liquid water could exist on its surface if conditions are right. This matters because liquid water is key for supporting life. It enables chemical reactions, helps regulate climate, and sustains ecosystems. But we don't know HD 40307G's actual conditions yet. Much depends on its atmosphere. A thick one could trap enough heat for liquid water despite the cooler star, while a thin atmosphere might leave the planet too cold, even in the habitable zone. The atmosphere's composition would also determine whether the climate stays stable long enough for life to develop. HD 40307G's discovery changes how we see planetary systems and life's potential in the universe. It proves super-Earths can exist in habitable zones and suggests many more might be out there. The fact that it orbits a cooler, smaller star than our Sun also broadens the types of stars that could host habitable planets. Life might not be limited to solar systems like ours. This planet also marks a new phase in exoplanet research. Its discovery has boosted interest in studying super-Earths, especially those in habitable zones. These worlds could teach us about conditions needed for life and reveal how diverse planetary environments really are. The study of HD 40307G and similar planets could shape future space missions and telescope designs as we search for life across the galaxy. Beyond its scientific value, this super-Earth has captured public imagination. The idea of an Earth-like but larger world in another star system sparks wonder about how life might exist under different conditions. HD 40307G represents both the vast possibilities of the universe and how early we are in the search for extraterrestrial life. Future research will combine spectroscopy and direct imaging to analyze its atmosphere and surface. Upcoming James Webb Space Telescope observations may reveal whether this planet could truly support life, or if it's another example of the universe's incredible planetary diversity. HD 40307G showcases how far exoplanet science has come while reminding us how much remains unknown. This cosmic rule-breaker, located 336 light-years away in the constellation Crux, shatters expectations about planet formation. With 11 times Jupiter's mass and orbiting 20 times farther from its star than Neptune does from our Sun, about 650 astronomical units, HD 106906b exists in a no-man's land of planetary systems. Discovered in 2013, its extreme orbit, where its star's gravity barely holds sway, challenges everything we know about planet formation. At this distance, far beyond our Kuiper belt, scientists never expected to find full-fledged planets. Its existence forces us to reconsider how planetary systems evolve, suggesting planets can form or migrate to unimaginably distant orbits. Though a gas giant like Jupiter, HD 106906b's lonely, far-flung orbit makes it utterly alien compared to anything in our solar system. This outlier continues to puzzle astronomers as they try to explain how such massive worlds end up in such extreme orbits. HD 106906b's wide orbit defies standard planet formation theories, which say planets form in the dense gas and dust disks close to young stars. Its extreme distance suggests either a different origin story or dramatic migration after forming. One theory is that gravitational kicks from other massive objects, like a passing star or giant planet, could have ejected it outward. But this usually creates stretched oval orbits, while HD 106906b's path is surprisingly circular, deepening the puzzle. Alternatively, it might have formed alone far from its star like a failed star, brown dwarf. This would make it more of a cosmic hybrid somewhere between planet and star, blurring the lines between these categories. HD 106906b's weirdness forces scientists to rethink how planetary systems evolve. Its existence hints at far more diversity in planet formation than we imagined. Over time, interactions with other stars or galactic forces could further disrupt its orbit. The discovery also impacts how we view our own solar system, if massive planets like this can lurk in other systems' outer reaches. Could something similar, like the theorized Planet 9, exist beyond our Kuiper belt? Studying outliers like HD 106906b isn't just about one oddball world, it's about uncovering the full range of what's possible in planetary systems. HD 106906b shatters our solar system-centric ideas about planets, proving the universe creates far wilder and more diverse planetary setups than we ever imagined. This oddball world reminds us our cosmic knowledge is still growing, with every new discovery ready to flip existing theories on their head. Since its discovery, HD 106906b has stayed in the scientific spotlight. Astronomers are throwing every tool they've got at it, studying its orbit, makeup, and backstory. The upcoming James Webb Space Telescope could be a game changer, potentially cracking the mystery of how this planetary misfit ended up so far from its star, and what it tells us about planet formation in general. Discovered in 2017, KELT-9b is where planetary science meets the impossible. This ultra-hot Jupiter, 670 light-years away in Cygnus, holds the record for hottest exoplanet, with surface temperatures hitting a mind-melting 4,000 degrees Celsius, 7,200 degrees Fahrenheit. That's hotter than some stars. KELT-9b orbits its massive blazing host star 100 times closer than Mercury does our Sun, completing a full lap every 36 hours. The radiation bombarding this gas giant is so intense it rips apart molecules in its hydrogen/helium atmosphere, reducing them to single atoms, blasts gas into space, creating a glowing, comet-like tail of escaping hydrogen. Cooks the planet to stellar-level temperatures, making its atmosphere behave more like a star's outer layers. This planetary inferno is a goldmine for scientists. By watching KELT-9b's atmosphere evaporate, we're learning how extreme radiation reshapes planets, clues about early Venus Earth, the limits of atmospheric survival in brutal environments. Whether this world is slowly vaporizing entirely, the big question? How long can KELT-9b last? While its massive size, it's a gas giant, helps it cling to some atmosphere. The relentless stellar fury means it's locked in a losing battle, one that might eventually leave nothing behind but a scorched core. KELT-9b's slow atmospheric destruction gives scientists a masterclass in how planets evolve under extreme stellar bombardment. This scorching world offers a unique window into star-planet interactions. The constant barrage of high-energy particles from its host star shows how radiation can shred atmospheres, a process that might occur on other close-orbiting exoplanets' atmospheric survival limits. Despite temperatures hot enough to vaporize metals, KELT-9b maintains an atmosphere while losing parts of it to space, revealing how planetary gravity battles stellar winds, unconventional planetary science. Its star-facing side reaches temperatures rivaling red dwarf stars, creating chemical conditions never seen in our solar system. The discovery of this hellish world through the KELT telescope survey proves we need better instruments to study extreme exoplanets. Future observations will reveal how quickly KELT-9b is losing its atmosphere. Whether it's forming unusual chemical compounds in its superheated air, what ultimate fate awaits planets orbiting so close to stellar infernos? KELT-9b forces us to expand our definition of planet and reminds us that the universe routinely defies our expectations. As new telescopes come online, this ultra-hot Jupiter will keep challenging our understanding of what's possible in cosmic evolution.